Welcome to the AP Physics lecture on the law of motion. Here we're going to talk about the weight and the apparent weight. The weight, by definition, we see that as the force due to gravity. All masses are surrounded by a gravitational field. The gravitational field exists in terms of a long-range force. It will accelerate. We call this the gravitational acceleration due to the acceleration due to gravity. Smaller mass towards itself. There is a more complex explanation on gravity, but think about the Earth as a one large mass, and any other masses are within its gravitational field, so objects will accelerate towards it. The moon and other planets have different values of its gravitational acceleration. The reason why is because they are of smaller mass. So their gravitational pull is going to be a different value. We experience a force of gravity that is always downwards towards the center of Earth because we are closer to Earth. So we experience Earth's gravitational pull. If we were on the moon, we would experience the moon gravitational force. When you sit down, the force of gravity does not disappear. It is just simply balanced by the normal force. However, when you are falling from an airplane, you are falling and you are accelerating downwards because the normal force isn't balancing you out. Hence why you fall. So here are two examples. A 60 kilogram object and a 100 Newton object. There are four categories. Please fill this out. So the mass on the Earth, a 60 kilogram is also 60 kilograms. Nothing changes. But what is the mass of a 100 Newton object? We just divide that by gravity, which gets us 12 kilograms. Let's look at the weight. What is the weight of the object? So what do we do with the 60 kilograms? Well, we multiply by the gravitational 10. So 60 times 10 is 600 newtons. So we would say this object has a weight force of 600 newtons. What about the weight of the 100 Newton object? It's 100 newtons. Newtons is already the weight of the object. What happens if we go to the moon? What happens to the mass of the 60 kilogram object? It doesn't change. You don't lose anything. Your mass stays the same. What about the 100 kilogram object? Does that mass change? No. It's still 12 kilograms. Your mass does not change when you go from place to place. The way your weight feels is different. So on the moon, your gravity is 1/6. That is of Earth. So you multiply 1/6 times your mass times the acceleration. And now you're going to see that your weight on the moon is 100 newtons. It's 1/6 of your weight on Earth. What about the 120 Newton object? Well, that's going to also be 1/6. So 1/6 times 120 is 20 newtons. Notice that your object that you feel lighter on the moon because, again, its gravitational pull is 1/6 of Earth. Let's talk about the apparent weight. Notice you cannot actually feel your own weight. An object cannot create a force on itself. When you feel force, you are actually feeling the push of an agent or the external object doing the pushing. Gravity is actually not a contact force. We see it as a long-range force. So how can you feel a force, which is gravity, that physically doesn't touch you? Well, you are standing, sitting, or laying down. You are actually in contact with the surface. As a result, your weight pulls you down into the surface, and accordingly to Newton's third law, the surface will actually push you back. The normal force of the surface pushing you back is the contact force, which you're capable of sensing. So here's you, here's the Earth. You apply a force of the student on the Earth is going to be the same thing as the force of the Earth on the student. What you're feeling is the contact force of the earth on the student. How do we calculate the apparent weight? Well, when you're stationary, the normal force acts upward is equal to the weight that pulls you downwards. What you're feeling and describing as your weight is actually your brain's interpretation of the normal force. At rest or at constant speed, the weight down is equal to the F support. What I mean by F support is the apparent weight. So we say that F net equals to 0, you are fully supported. If we subtract the F support to the other side, we saw that it is in the same magnitude, just in opposite direction. So we would say that your force is the weight is equal to mg, which is equal to the F support. Again, F support is your apparent weight. Under these normal circumstances, you feel your normal weight. This is what you're feeling. You're in every single day life. However, normal force and weight are not always equal. This means that the human can be tricked into feeling heavier or lighter. The appearance of a weight that is different from an actual weight is known as the apparent weight. Let's calculate the apparent weight. Apparent weight differs from real weights when objects are accelerating. There are two categories, and these are the two common ones that they use on the AP exam. One, if the acceleration of an object is given and is different than 9.8 meters per second squared, simply multiply that object's mass by the acceleration. Here is an example. An 80 kilogram astronaut experiences a 5g of acceleration during a spaceship launch. What is the apparent weight? So here you just multiply 5 times 9.8. That gets the new acceleration. So 5 times 9.8 is roughly like 49. You could round it up to 50. Okay, that is the amount of G's that you're pulling. 50 meters per second squared. We multiply that by the mass, which is 80, getting you 3,920 newtons. This is the apparent weight. If the object is actually in contact with the surface, all we do is we solve for the normal force. You're going to see the examples in the next slide. Before we do that, we have to talk about the diagram here. A free body diagram for a person in contact with a surface that is accelerating vertically is the same for both upwards and downwards motion. Here's the exception. When ropes are involved, tension replaces the normal force as the variable that equals to the apparent weight. This means that if we sum the forces is also the same as are most of the steps in solving for the normal force. So here, the summation of the forces in the y direction is the normal force going up minus the force of gravity going down. We solve for the normal force by adding Fg to the other side. So normal force equals to Fg plus summation of F. Summation of F equals to ma. Mass is in mass is the same for the person, and the G and the A is the M factors out, so there's a parentheses G plus A. The way I think about this is that this is the mass of the person, or the mass of the system, and this is going to be the this is going to be the mass of the system, and this is going to be the mass of the system. The acceleration of the system. And again, here the acceleration of the system is a combination. You can either have adding the acceleration, subtracting the acceleration. So let me show you what I mean. So if the object is moving up and speeding up, you would say it has a positive acceleration. So you're adding more acceleration into the system. Or you could say it's going up, but it could be slowing down. If it's slowing down, the acceleration would be negative. Then you could also have constant velocity or stationary. This is when a equals to 0. So you could either add acceleration for speeding up, subtracting acceleration when it's slowing down, or a equals to 0 when it's at constant velocity or stationary. Here are the three scenarios. If you are leaving the first floor and you're accelerating upwards, then afterwards you're moving at a constant velocity. Then when you're near the 10th floor, you decelerate at 2 meters per second squared. Okay, let's look at the problem first of all. The first scenario, you are accelerating upwards. So the summation of the forces equals equal to ma. In the middle scenario, it is constant. So the summation of the force is equal to 0. And lastly, you're decelerating, but it's still summation of F equals to ma. The diagram just shows the object going up and down. But please understand that the net is going to be completely different. So let me draw it for you. So the first one, if it's accelerating upwards, it should be longer than down. When it's constant, it is equal. And when it's decelerating, the bottom has to be longer than the going up. Okay, so this is how it will normally look like for the with the proper lengths. Okay. So summation of the force is still the same. All we have is the normal force minus the force of gravity. We did the math from before. If you would like to see it, all I did here is I substitute this to mg equals to n minus fg. Add fg to both sides. I get fg plus m. So this is a. ma equals to n. Fg is mg plus ma equals to n. Factor out the common term of m. You should get m g plus a equals to n. All right. So if you are accelerating up, the a, you're going to be adding the 2 meters. So it becomes n is equal to 50 parentheses 12, right? 10 plus 2. If it's stationary, you add 0, so it's the same. 50 times 10. And when it's slowing down, you subtract, which is just 8. So it's 50 times 8. Notice that this is the normal, right? This is normal. This is the normal weight, right? You're going to, here, it's 600 newtons, so you're going to feel heavier. And when you're slowing down, look, it's lower than the 500, so you are going to feel lighter. Let's take a look. We already seen this one before, where this is perfectly balanced. So that was the first one that I'm referring to. This is when the object is at equilibrium. Your apparent weight you feel as the normal weight. If you're accelerating up, we saw that it is 50 times 10 plus 2, which is 600. You feel heavier. The reason why here is because your object is accelerating up. If you look at the vector here, your F support has to be longer. Okay, that makes sense. Because your F net is going up forward. So here, your apparent weight is your weight plus the mass times acceleration. The extra acceleration comes from the object accelerating up. Please understand that when accelerating upwards, you feel like your weight is greater than the normal since the required supporting force by the elevator floor is greater than the normal. The support must supply an excess over the gravitational force in order to accelerate the object upwards. When you're decelerating, you actually feel lighter, which is 400. The reason why is because now your F support is going to be smaller because your MA goes down. So do you see the vector of your F support has to be smaller? Your F net is going down because you're accelerating down. The F support here is smaller, so it's W minus MA. It's a subtraction because, again, that is the minus 2. You see that when accelerating downwards, you feel like your weight is less than normal since the required supporting force by the elevator floor is less than the normal. The support is less than the normal, permitting your body to accelerate downwards. Lastly, we're going to go over a short answer. Given this scenario in 5-6, and here's the scenario. So you put an object on a scale and by a string, and that string is attached to a scale here. right? Like the ones that you have in the grocery store. And based on its weight, it's going to move down the ruler. It's going to show how much it weighs, okay? This is a traditional spring scale, all right? The heavier it is, right, the more the spring is going to be stretched. So the more it's going to go down the scale, showing it's a heavier object, all right? So put this whole system, like this whole scale, on an elevator. And the elevator begins at the 0th floor. Here's the building. And you begin at the 0th floor. At the 0th floor, you accelerate it upwards. Then in the middle, you had constant acceleration. And when you go to the top of the 10th floor, you begin to slow down, right? Because you have to stop. Okay? So again, the elevator begins from floor 0 and accelerate upwards to the 10th floor. During the middle of the elevator ride, the elevator stops accelerating and maintains a constant velocity. As it approaches the 10th floor, the elevator decelerates to slow down and stops on the 10th floor. Describe the length of the spring during the entire situation. Give this a try. There are 3 scenarios, so make sure you have 3 short answers. When the elevator begins from floor 0 and accelerating upwards to the 10th floor, the length of the spring will increase because there is an addition of the elevator acceleration to the entire system's acceleration. So the spring is going to stretch more. That's what I mean by the length of the spring will increase. So you could also use the word stretch more. That is due to the acceleration of the system increasing. The acceleration from the elevator increasing the system's acceleration. When the system is in equilibrium, that's when the elevator maintains a constant velocity. The length of the spring will be at equilibrium because there's no addition of the elevator's acceleration to the entire system's acceleration. So here it's just mg. There's no adding anything. It's just add 0. So the length of the spring will stay neutral. It's exactly like how it was outside of the elevator. Next, the elevator begins to decelerate. When it decelerates, the length will decrease, showing that it is lighter because there is an addition of the elevators decelerating to the entire system. That's why it's minus a. So this is what a apparent weight question would look like on the AP exam in terms of either free response or multiple choice. Here's some notes for the apparent weight as some side facts. Astronauts in space experience weightlessness, however they propose mass and are pulled to Earth by the force of gravity. Therefore, they have some weight. Even though they are in space, they are still very close to Earth. So, surprisingly, the pull of gravity acts on an astronaut orbiting Earth is slightly just lower than it is on Earth. So, why do they experience a feeling of weightlessness? Well, in orbit, the astronaut and their spacecraft are actually falling towards Earth. Earth is actually in free fall together. Since they are falling at the same rate as the spacecraft, the surface in the ship cannot create a contact force on the astronaut. With no normal force to give the astronaut a sense of weight, they feel weightlessness, despite actually having weight near the same as on Earth. If the spacecraft continues to fall, what is preventing it from crashing into Earth? Well, when a spacecraft actually has the correct orbital speed, it is tangent to the velocity, combines with the vertical free fall to create a projectile motion. Again, this is going to make more sense when we talk about our elliptical orbits. So, you don't need to go to space. You could actually go to an amusement ride. Any amusement park ride that causes you to feel to lose contact with the surface would normally. Any amusement park ride that causes you to lose contact with the surface that you would normally be touching will make you feel temporarily weightless. I can pull up an example for you. If you go to Disneyland, there's the roller coaster in the their loop. Okay, so during the loop, during this part of the Disneyland ride, when you are right here, you feel like you're being pulled, and you're gonna feel weightlessness when you're coming down. All right. Also, if you ever have gone to Six Flags, there's a Superman ride at Six Flags. Okay. Where you go completely up, right? That would also be a good representation, okay, of how you would lose contact with the surface and feel weightlessness. All right. But there you go.